Hey everyone, welcome to Theory Lunch. We have Siddharth to talk about learning to cut in integer programming today. And food theory is sponsored by Smart Contract Research Course. Okay, go ahead.
Okay, thanks everyone for coming. So the title of my talk is Learning to Cut in Integer Programming. It's based on joint work with Nina Balkin, Thomas Sandholm, and Ellen Vittersick. And the results I'll talk about come from 3 papers that we wrote together, one of which was a spotlight at NeurIPS last year, and the other 2 are preprints that are on arXiv. Okay, so integer programming is one of the most expressive methods of writing down a vast array of discrete optimization or combinatorial optimization problems. And it has applications in a ton of different fields, like scheduling, routing, auction design problems, many different problems from machine learning, like clustering, and so on. So in this talk, I'm going to talk about cutting planes, which are a very important component of integer program solvers that are really responsible for some of the breakthrough speedups of integer programming solvers in the last 2 to 3 decades. And you know, I'll define these very shortly, but you know, at a high level, these are just specialized constraints that you add to the formulation of an integer program to try to tighten the formulation. And there are tons of ways to configure how these modern state-of-the-art integer programming solvers like Cplex and Gurobi choose cutting planes. So they offer many ways to tune these parameters and when and how many of these things to add. In this talk, I'll be talking about the first formal theory for using machine learning to select cutting planes. So I should say that, you know, the study of when to add cutting planes, what cutting planes to add, it's really not an exact science. People don't really understand how to do this. There's not very many, you know, formal guidelines on how you should do this. And recently, a line of work has emerged on using machine learning to try to see if these things can yield, you know, speed ups in practice. So we are in that line of work and present the first formal theory in doing this with provable guarantees. Okay, so the first thing to talk about is branch and bound. Branch and bound is a powerful tree search algorithm that's used by all the commercial solvers to solve integer programs in practice. And branch and bound uses the linear programming or LP relaxation to do an informed search throughout the set of feasible integer solutions. So, you know, if you have an integer program of this form, LP relaxation is just obtained by dropping the constraints that the variables must be integral. Okay, so now I'll give very quick high-level description of how branch and bound works. So, you know, branch and bound is a tree search algorithm. At the root of this tree is the input of the original integer program that you start with. At every step, you choose some variable to branch on, and you generate the following 2 subproblems. And you know, the way you generate these subproblems is based on the solutions of LP relaxation that you get at this root. And know that it's important to do it in this way, you know, because if you partition the space in any other way on this variable xi, it's necessary that one of those branches you're not going to have made any progress. So it's important really to partition the space based on this LP guidance that you're getting. Okay, right. But now, of course, you know, you don't want to build this whole tree, this huge tree with many nodes. And so what makes branch and bound effective in practice is, you know, it's pretty smart in how it prunes the subtree. So there's a few reasons why you might stop the search at a given node. Well, the first reason is if the LP relaxation at that node is infeasible, you stop searching, there's nothing more you can do at that node. If the LP relaxation is integral, then, you know, you can also stop your search at that node and save that integral solution for later. And really the most critical aspect is this bounding aspect, which uses the LP guidance to say, you know, at any given node, if I solve the LP relaxation and the objective value I get is worse than the best integral solution I found so far, well, I don't need to expand the subtree at that node further. I can stop the search there. Now, I should say that, you know, I in the previous slide, I said you choose a variable I to branch on. That itself, choosing which variable to branch on is also a whole other topic that a lot of people study, but that's not something I'm going to really talk about here. Similarly, which node to explore next in the branch and bound tree, also something that requires some nuance. I won't really go into that either. Okay, so branch and cut is a refinement of the branch and bound algorithm, where at each node you may add these cutting planes. And cutting planes, as I'm going to define in the next slide, are just a method of getting tighter LP relaxation bounds with the hope that you can use these better bounds to prune the subtree sooner and finish the search with a much smaller tree. Okay, so what is a cutting plane? Cutting plane is just an additional constraint that you add to the formulation. It's just a constraint that does not cut off any integer feasible points. So on the left, all these green lines are valid cutting planes. On the right, this red line is not a valid cutting plane because it chops off an integer feasible point. Yeah, and these things can be useful because if you add a valid cutting plane and it in particular cuts off the LP optimum of the LP relaxation, then you've made some progress in these LP estimates. And like in this picture, maybe the LP optimum is at this blue vertex. After you add the cut, well, the new LP optimum is somehow much closer to the true integer optimum, and maybe that will allow you to speed up this search. So to really drive home that point, if you're very lucky and are able to somehow get really good cutting planes, then you don't even, in this picture, if super lucky and you add these two cutting planes, you're done before even running branch and bound. You solve the LP relaxation, and great, the vertex happens to coincide with the integer optimum, you're done. But this kind of thing is really just not possible in practice. And when I say not possible, like really computationally hard, and just it's not tractable to find such cutting planes. Okay, so one famous family of cutting planes that are very easy to and fast to generate are the class of Kvatal-Gomery or CG cuts. And these are just parameterized by a vector of multiplier defining the integer program, and they're guaranteed to be valid. So just quick intuition is how this thing is derived. AX is less than or equal to B, that's just the original constraint matrix. UAX less than or equal to UB, well, that's still fine. You're just taking a linear combination of them. You can round down the left-hand side because you're just making it smaller. And then since you only care about integer feasible points, left-hand side is always integer for every integer feasible point. So you can round down the right-hand side too. And for such a simple procedure, you can generate these things from the simplex tableau after running a simplex algorithm to solve the LP relaxation. You can generate these things very, very quickly and guarantee that they actually cut off the LP optimum at any node in the branch and cut tree. So you can kind of guarantee by adding these things, you are making some progress with these LP estimates. Okay, so I'll now talk about some history about cutting planes. So these like Kvatal-Gomery cuts were kind of introduced in the 1960s by Gomery, and he actually showed that you can use these cuts to give a finite pure cutting plane algorithm to solve any integer program. And what I mean by this is there's no tree search, no branch and bound. It's just an iterative algorithm where you solve the LP relaxation, you add a bunch of these cuts, you resolve the LP relaxation, you add more of these cuts and keep doing that. And eventually that'll actually terminate such that when you solve the LP relaxation, you'll get the integer optimum. But this is a very inefficient procedure. Number of cuts it can require to terminate can be a ton, maybe exponentially, or maybe even worse. Yeah, and these kinds of general purpose cuts, and when I say general purpose, like these CG cuts, you don't need to know anything about the structure of the integer program to generate them. And these kind of general purpose cuts were thought to be practically useless for decades. And the thought was, since they don't exploit any underlying structure of the integer program, like if you have an integer program coming from some graph problem or some knapsack problem, they're sort of cuts that you can write down after really staring at the structure of this problem. And these cuts don't do that. So people thought they were kind of practically useless. And here's some quotes from some big players in the field at the time. So Nemhauser and Rolsey said, these cuts don't work well in practice. You need an extremely large number of them for convergence. Padberg and Rinaldi said these cutting planes have poor convergence properties, furnish weak cuts. And they even said marriage of classical cutting planes and tree search is out of the question for large-scale combinatorial optimization problems, which is very, very opposite from what is true today. And Gomery himself even had a low opinion of the practical use of his cutting planes. as of the early 90s. But so this kind of belief took a drastic, it drastically changed in the mid to late 90s when Ballas, Seria, Cornijoles, and Nutraj released this paper, where really they kind of said, that okay, the purported failure of these Gomery cuts really boiled down to just poor implementation choices that these previous papers had tried. They either tried it in like a pure cutting plane framework, or they do things where they added a single cut, would resolve the entire LP, then add another cut, resolve the entire LP. So they were doing things like that. Whereas these four authors, I guess actually from CMU at the time, figured out generating these things quickly from the simplex tableau, adding a bunch of them, and then using it in conjunction with the branch and bound tree search was very, very fast and achieved really remarkable speed ups. And this is how the state-of-the-art modern solvers all work today. So if you run Cplex or Gurobi on some problem of your choice, they're going to be adding these Gomery cuts throughout the tree. Yeah. Okay, so now let me jump into the first part, of what I'm talking about today. And that is the structure and sensitivity of branch and cut. And in this part of the talk, I'm going to look at kind of fundamental question, which is, can we understand how the branch and cut tree, the execution of branch and cut, behaves as a function of cutting planes that you add? Okay, so the first thing is that the branch and cut tree is very sensitive and volatile. It is very sensitive and volatile to even minute changes in parameters defining cutting planes. So this is a fairly simple example where it's an integer program that's infeasible, but the blue line is its LP feasible region. And it's known that for this this integer program, I'm not giving all the details, that a vanilla branch and bound approach that doesn't use any cutting planes or heuristics will basically need to branch on every single variable to determine infeasibility. So it's going to build an exponentially large tree. Now in this picture, on the left, what I've drawn is a Kvatal Gomery cut given by this dashed line. It's a valid cut, almost just vacuously, because there are no integer feasible points. But then once you add this cut, they'll empty. So then once you run branch and bound, it'll just finish at the root, and the LP will also be infeasible. Whereas on the other side, if you add the dashed line, then it's not doing anything and you're not making any progress with respect to the LP feasible region. You add that cut, is going to build an exponentially big tree. Okay. And graphically, you can visualize this in the space of the parameters defining the Kvatal Gomery cut. So this was an integer program with two constraints. So there's exactly two parameters defining the possible CG cut. And you kind of can draw this in the space of U1, U2 parameters. And it's just like a threshold, just a line dividing the space. The parameters come from one side of the line, branch and bound finishes immediately. Builds a tree of size 1, comes from the other side, you get an exponentially big tree. Okay, so that's one thing that minute changes in these parameters can lead to wildly different behaviors. But really, now the question we're going to try to tackle is, well, is there some structure that we can pin down on this branch and cut tree? Like in the previous picture, even though the behaviors were very different, there were only two different behaviors coming from, and you could write down this line defining space saying, in one region it looks like this, in the other region it looks like this. So can we say something general like that about these Kvatal Gomery cuts? And yes, we can. So we prove that given any integer program, there are this many hyperplanes that partition the parameter space of CG cuts, so 0, 1 to the m. There are a bunch of hyperplanes that cut the space up, such that if you look in any one of these connected components formed by these intersecting hyperplanes, as you vary this like vector of multipliers, as you vary it within any given region, the actual cutting plane constraint that gets added is invariant. So as you vary u within this region, the actual cutting plane you get is invariant, and that immediately implies that branch and cut, of course, is invariant. So this is something a bit stronger than just looking at branch and cut. Okay, so I'll give the proof, which is quite straightforward. It's just really looking at this rounding procedure that's going on in this CG cut, right? So, okay, just recall the CG cut parameterized by u is this guy. So the floor of ua times x less than or equal to the floor of ub. Now, for any u and any column of the constraint matrix AI, this like ith coefficient is bounded in magnitude by just the one norm of this column. That's just because u is constrained to between 0 and 1. Now, of course, you're rounding this down, so this coefficient is an integer. So let's just write down what it means for this coefficient to round down to a particular integer ki in this interval. Well, it means that its uai must be sandwiched between ki and ki plus 1 for it to round down to ki. But writing this down, these are two half spaces in u, right? So ki less than or equal to uai is a half space in u, and uai less than ki plus 1 is also another half space in u. And you put all these half spaces, or whatever the hyperplanes defining these half spaces, you put all of them down for every integer in this range. You do that for every column I. Then in any region defined by the intersection of these hyperplanes, as you vary u, all of these coefficients are the integers that they round down to are going to be fixed in that region. So then doing the same argument for the b term gives this result. Okay, so that really used a very specific structure of these Scott-Montgomery cuts, that they're rounded down in this very specific way. So now I want to ask maybe even more fundamental question. Given two valid cutting planes, so these are just two constraints we're considering adding to the integer program, when does branch and cut behave identically on these two integer programs? And the way I'm going to answer this is going to be similar to what I just did. I'm going to come up with some partition of the space of alpha and beta parameters. So there's this n+1 dimensional space. I'm going to come up with some partition of that space such that, in each connected component of that partition, as you vary alpha and beta, branch and cut, its execution is going to be identical, and the tree it produces is going to be identical in each region. And this is going to take a bit more work than the result for Scott-Montgomery cuts. So before I get started, I'll just flash the result first. Is that it's given by this polynomial, a bunch of these polynomial surfaces, and there are quite a lot of them. But the second part of the talk, I'm going to kind of apply this to get some sort of sample complexity results. So you don't need to worry. All of this will get passed through a log, and the goal is to get polynomial like generalization guarantees. But this is I figured I would present this as a self-contained kind of structural analysis of branch and cut. Okay. Okay. So there's a bunch of polynomial hypersurfaces that are defined in n+1 variables, alpha and beta. And if these things, you look at all their zero sets and look at any connected component that they induce, then the branch and cut tree is going to be invariant. Yes. Oh, that's a good question. No. So really, you can think of 5 as maybe like 2, and there's something special about 2. The 5 comes from the fact that we ran this analysis for a very specific branching rule that selects variables. So it's a commonly used rule in practice, and that thing is a bit messy. So that's maybe just an arbitrary choice that we use to write this result up. But if you think of the branching rule as being very naive, like some lexicographic thing where it branches on x1 first, then x2, then it would just be a degree 2 polynomials or something. So yeah, not important for this talk, but yeah, I mean, the 5 is not like arbitrary, it comes from analyzing this particular variable selection rule.
Can you say, what do you mean by the cut is invariant over all the
Yeah. So okay, remember, so this is, it means that, okay, like look at one of these integer programs. And actually, yeah, good that you asked that. So there's a few details I should mention. we're looking at a very simplified scenario where we're adding a single cut at the root of branch and cut. So really, this is more like cut and branch. So we're adding a single cut to the integer program, running branch and bound, and then seeing what happens. And the question we're asking is, can we understand the branch and cut tree as a function of alpha and beta? Right? And here we're saying, well, yeah, it's like piecewise constant, basically. But piecewise constant over this huge space. Yes.
Wait, so obviously whether the trees are different, sort of depends on which tiebreaker you're using to choose how to branch. So is this saying for any choice of the exact algorithm, this is true, or is it saying there is a choice of the exact algorithm for which this is true?
So if you're asking about the branching rule specifically, this is stated for a particular branching rule. And of course, yeah, the result you get will change a bit based on maybe what branching rule you consider. So there's definitely not going to be a universal partition such that no matter how you branch and stuff, it's going to be invalid.
Yeah. No, I knew that. I was just wondering if you could say no matter which rule you choose, this theorem holds. But okay,
Probably not, because if I really wanted to be devious, I could encode some arbitrarily complex function into the branching rule and do something silly and cause it to oscillate always or something. Yeah.
So before we were looking at the CG cuts, they have these explicit for functions.
Yeah,
And now we abstracted.
Yeah.
Does the representation of how we encode the branching rule matter, or do we just care that it is linear? There's some parameters out there.
So I think I more or less understand what you're asking. And so the first thing is, yes, we're abstracting away and saying before the CG cuts had this very particular form. It had these parameters u, and then it told you once you have a u, it tells you how to combine them around it, and then you get a particular alpha and beta from that. And here I'm abstracting away and saying, let's just say you're adding some constraint, then what happens?
Okay, so we can think of this as sort of like a generalization of the last one. The last one was if you have these unusually nice cuts, you get these unusually nice.
Yeah.
So in this proof, do you use anywhere that it is a cut? I mean, alpha x less than or beta it removes.
Yeah. So we'll assume, and this is maybe a little unrealistic, but we'll assume that if you add an invalid cut, something just bad happens. And in practice, adding invalid cut is bad news because it's not going to be able to tell that you're adding something invalid. But in practice, you would never add a cut like alpha and beta. You will use something like a CG cut, which is guaranteed to be invalid. Yeah. Okay. All right. So then I'm going to now go through a few slides that sketch some important components in deriving a result that looks like this. Oh yeah, and I mean this tau thing is just tau appears in bound, but you don't need to worry. It's not making it any worse, any more exponential than it already is. It might become like n to the n cubed, but once we take a log, we'll get a polynomial sample complexity bound. And I mean it's a little subtle because if you're bad about actually, never mind. I won't, yeah. If you're not careful, you could count this in a bad way and get a doubly exponential partition. Okay. So the first thing I'm going to do is work through this example where I want to now answer a very basic question, which is I have an LP and I add another constraint to it. What happens to the new LP optimum? Okay. So this is a simple example with two variables. Maximize x plus y subject to x being at most 1, y being at least 0, y at most x. So the feasible region is this triangle. And the LP optimum is at the vertex 1, 1. And suppose we add a cut of the form alpha 1 x plus alpha 2 y is less or equal to 1. I'm just taking beta to be 1 for simplicity so we can visualize in 2D. We're going to come up with some partition the alpha 1, alpha 2. Okay, so we can compute these intersection points explicitly. So the intersection of the diagonal looks like 1 over alpha 1 plus 2, 1 over alpha 1 plus alpha 2, 1 over alpha 1 plus alpha 2, and the intersection of the vertical line looks like that. And already we can put down some conditions saying we want the intersection point to actually be in this triangle, can't be far off on the diagonal line. So these just asking that they satisfy the LP constraints will do that. And these are already some constraints on the alpha 1, alpha 2 that is going to create some partition of the space. Okay, next thing we'll do is write down what I'm calling an objective indifference curve, which is just, I want the set of all alpha 1 and alpha 2 such that the objective values on the two intersection points are the same. Okay, well, we can just write down what that is. So the objective value in the diagonal point, it's x plus y, so it's sum of the two coordinates, it's that. And yeah, so this is the surface you get, and rearrange it, it factors into these two linear terms. And the important thing here is that you get, well, two, I mean, it's not really two, but you get regions where if the equality is replaced by greater than sign, that corresponds to alpha 1, alpha 2, the LP optimum is on one of these edges. And if it's a less than sign, it corresponds to the other edge. And I'm not gonna worry too much about tie breaking and stuff, just fix some, it doesn't matter, this is the point, it's at both of them or whatever. Okay, so now we can visualize these things in the space of alpha 1, alpha 2 parameters. So now this here, the x-axis corresponds to alpha 1 and y-axis corresponds to alpha 2. The blue region contains all alpha 1, alpha 2 pairs such that those two intersection points indeed are inside the LP feasible region. And these two red lines are basically this, means a degree 2 surface, but it factors. So these two red lines correspond to that. And now you see this blue region, which is what we care about, is getting cut into two pieces by the red lines. And in one piece, and basically the thing is we can now write down the closed form for the LP optimum in each of these regions. And we already calculated these intersection points, but now we have this piecewise decomposition. In one of the regions, the LP optimum looks like this because it's always on the vertical edge. And in the other region, it looks like this because it's always on the diagonal edge. This example clear? Okay. So now I'm just going to run through that same example, but just in more generality. So in general, the LP feasible region is some polyhedron or polytope P, and say this blue vertex is the LP optimum. Okay, we had a cut. That means the new LP optimum is going to be at one of these two edges or two vertices. Yeah, so it's the new LP optimum is on an edge of this LP polytope, and in particular, any edge of the LP polytope can be identified with some subset of n-1 constraints, or more generally, dimension of p-1 constraints that are binding. Okay, well, now this cutting plane alpha x less than equal to beta is going to form a vertex with an edge, if all of these things are satisfied at equality. So if this system has a unique solution. Okay, well, if it does have a unique solution, then that intersection point is just given by Kramer's rule. So this is just the same thing that was going on in the example, but just writing it down a bit more generally. So this is an n by n matrix. Okay, so now let's write down that same sort of objective indifference surface, but for these two edges. So, we now have a closed form for, okay, if this cutting plane were to intersect those two edges, this is how the intersection point would look like. So we can write down what does it mean for the objective to be exactly the same on those two edges. And it's just this surface. And this is a degree 2 polynomial in alpha and beta, just because in all of these determinants, the alpha and beta stuff only appears on the last row. And on one side of the surface, by side, I just mean, replacing the equals then with the greater than or equal to is going to correspond to all alpha and beta such that the LP optimum is achieved, say at on edge E1. And flipping the sign is going to correspond to the other edge. Okay, so now here's where I'm just going to hand wave and generalize the rest of this to make it all work, which is, you do this for every possible edge of the LP polytope. So you do this for every possible pair of edges of the LP polytope, sorry. And you do this for every possible pair, put all these surfaces down, and then in every component, as you vary alpha and beta, the edge of the LP polytope at which the new LP optimum is achieved is going to be an invariant. That edge is going to be invariant. And if that's edge is invariant, then we know what the LP optimum looks like. It's just this thing given by Kramers. So the point is, we now have this like piecewise decomposition such that we have a good handle on what the LP optimum looks like as a function of alpha and beta, which is going to be useful. And then also importantly, you can extend this reasoning to refine this partition further, such that not only do you get a handle on the LP optimum at like the root, but you get a handle on the LP optimum at any possible node of any possible branch and cut tree. So, and what I mean by this is, branching constraints have a very particular form, and you can kind of enumerate over distinct subsets. And it's really not counting subsets because, some branching constraints will be redundant. So you can count this in a reasonable way to really get a partition such that as you vary alpha and beta, you have a handle on the LP optimum at any possible stage of any possible branch and cut tree. Okay.
So is that why you said wrongly counting the lead to W exponential?
Yeah, that's probably, that's the part that if you don't take into account that, like, if you have a branching constraint, xi less than equal to 5 and xi less than equal to 7, obviously the xi less than equal to 7 is redundant, right? It's so if you don't take that stuff into account, then it can be, in the worst case, maybe doubly exponential. Or I mean, it can't be doubly exponential, but if you count it naively, then what you will write down might be that. Okay. Okay, and just for the sake of illustration, we drew this, we plotted the surface for some example LP with 3 variables. In the previous example, the quadratic thing factored. So this to show, it actually is quadratic and not something that always becomes lines in the end or hyperplanes. Okay, so now equipped with this handle on how the LP optimum looks, we can now kind of pin down how every step of branch and cut algorithm is going to be affected by changes in the cutting plane parameters. And I'll go through this very quickly, but you can kind of just imagine, when you do branching, these are the 2 subproblems we generate. We want those 2 subproblems to be like invariant within any given region. So, and now we have a handle on what this X star of LP looks like as a function of alpha and beta. We can control the rounding thing pretty easily and do some stuff with hyperplanes and get a handle on the branching stuff. And yeah, Brian asked about the 5, and that comes from just handling a different, like a more sophisticated variable selection rule. Okay, the next step is to handle pruning due to a node having an integral LP relaxation. And this I'm really gonna go over very quickly and not give much intuition, but it's just, you want to refine this partition such that at every stage of branch and cut, if for some alpha and beta in your region, if at some node it's pruned because the LP optimum is integral, then for every alpha and beta of that integral, that pruning decision because of integrality should be the same. And in particular, the integral point at which that optimum is achieved is going to be the same. Okay. Okay, and the key takeaway at this point is that if you were to run branch and cut, but suppress the bounding step, so suppress the step that uses LP estimates to cut off nodes, then we're actually done at this point because we've achieved the partition where as you vary the cut parameters, the tree is actually going to be identical because all the branching decisions are going to be the same everywhere. And if you ever prune a node due to being integral, that integral solution is going to be the same for every alpha beta within a given region. Okay, and then finally, once again, I'm going to go over this quickly to handle that important pruning step. Once you know that this bounding suppressed branch and cut tree is invariant, you can zoom in on one of these regions in the partition and say, well, regardless of alpha beta in this region, we can write down this invariant ordered list of nodes expanded by branch and cut, and this kind of list of nodes is going to be the same. And we can track, when are integer solutions found. And we can just go in for every node and say, well, let's just put down a condition that says, what does it mean for, at this node, the LP relaxation to have an objective that's equal to the objective of the best integer solution found up until that point. Then if we do that, at that node on one side, the alpha and beta from one side is going to represent those where that node will be pruned. And then on the other side, it won't have been pruned. So, if that wasn't clear, that's it's fine. I didn't want to spend too much time on this, but really the key takeaway is that, this coming up with this piecewise decomposition where we were able to understand how the LP optimum looks at every node as a function of the single cut you add at the root of the branch and cut tree, it allows us to go and unwrap all these steps of branch and cut and write down very explicitly everything that's going on. And all these conditions are like some degree 2 surface or hyperplane or something. Okay, and so that's the end of that analysis, and this was the result I showed to begin with. Okay, are there any questions? So I'm gonna now move on to the second part of the talk, which is applying all this. Okay, great. So in this second part, I'm going to talk about generalization guarantees for cutting planes. So in particular, this idea of distribution-dependent cut selection if you're kind of solving integer programs that come from some distribution of typical integer programs. So the motivation here is that, like if you're an airline scheduling company and you have some day-to-day, you're doing some optimization form of integer programming, then maybe the best cutting planes to speed up the types of integer programming you're solving are not going to be the same ones that are useful for like auction design integer programs that some sourcing firm is solving on a day-to-day basis. So concretely, this is just like a standard back learning setup where maybe there's some unknown distribution D over integer programs, and can we prove a sort of generalization guarantee? So if you see a bunch of samples and you know that like this particular kind of way of choosing cuts is really good on the samples, like it's fast on average or leads to small tree sizes on average, can you expect that to generalize to a new unseen future input? Okay, so and it turns out that I like really did all of the heavy lifting for this. These are all very immediate from these sort of structural results. So for Montgomery cuts, there the situation was a bit simpler where really, even though this U comes from this continuous space and there's an infinitely many number of possibilities for U, there were really only like a finite number of behaviors, finite number of cutting planes that really resulted. And this is like a very standard kind of pack style guarantee, where if you notice here, so is saying that uniformly over all Montgomery cuts, the difference between the empirical performance and the average the true expected performance is bounded by this generalization guarantee. When I say performance, you can think of something like runtime, but to make this really rigorous, we were thinking of things like tree size, where you can really kind of quantify these things. So like we were proving that the branch and cut execution is invariant, and doesn't necessarily mean the runtime is going to be the same. That's
Is this for the scenario where you make one cut and then branch from then on?
Yeah. So all of this is there, but we had, in the papers we have generalize this to whatever you want. So many cuts at the root throughout the tree.
Yeah. You also have results for those.
Yes. Yeah. So this is right. So these results are all for the simple case where you had a single cut at the root and then branch out. Yeah.
The only thing that was hiding the probability.
Yes. Yeah. So right. So this is a guarantee that holds with probability at least 1 minus delta over the draw of the n samples to the training set, and like all you incur is some like plus log 1 over delta inside the square root. Yeah. Yeah. So h, it's like you view it as like just a limit on how long you're willing to run branch and cut in a sense. So this is like, this is something that's like common in this algorithm configuration literature when people provide these theoretical guarantees to say, in the worst case, if you're studying something like tree size, maybe without such a constant h, it could be really bad. So, and it's like an interesting, it's a cool open question, I think, to like connect this practice and theory to make it a bit more meaningful. But yeah, how people do it when they provide these kind of guarantees is like, okay, if you're solving this huge integer program, in the worst case, the tree could be like unimaginably big, and you're never going to let it get that big. So we'll assume you cap it off at some constant, and that's the term that is going to appear here. And yes, I mean, if you want this to be as like smaller than epsilon, n is going to now depend on h, which is maybe not the best thing, but I think it's a good research question to reconcile that. Okay, and yeah, the key thing here was that the number of hyperplanes in this decomposition, that's what is coming inside the log, and then the dimension of the space M is what is outside the log. Okay, now, so I haven't said what Gomery mixed integer cuts are at all, but basically Gomery mixed integer cuts are kind of a strengthening of the Vatal-Gomery cuts, and Gomery mixed integer cuts are really what this Balas, Seria, Cornish-Doles, Natraj. These are the family. This is the kind of cuts that they use to really see these breakthrough speedups. So very, very, very important family of cuts in practice. And these cuts, it so happens, they don't have that nice property of CG cuts where there are really only a finitely there are only finitely many actual cutting planes you can get. This is truly like an infinite family, whereas you vary the number of different cutting planes you could be adding, that's like a continuum. And to analyze this is where we really use that structural analysis that I spent most of my time talking about.
So should we think about these norms as being upper bounds on that?
Oh, yeah. Thank you for pointing that out. So yeah. So this is like a slightly just abuse of notation to make this easier to present. Yeah, this is over a distribution of integer programs. So there's no A and B. But yeah, it's just the distribution over integer programs that have a bound on the 1, 1, 1. Yeah, thank you. Okay, so now I'm gonna talk about something, trying to make this a bit more practical. So, in practice, I've been talking about like a single U that parameterizes CG cut and reusing that for a bunch of integer programs. In practice, though, that's maybe not the best idea. Like, it's guaranteed to be valid, but it's not guaranteed to cut off the LP optimum of a new integer program. So really, in practice, solvers use various heuristics and scoring rules to choose between a pool of possible cuts. For example, already, if you solve the LP relaxation and generate these CG cuts from the tableau, that already will guarantee that they cut off the LP optimum. So I'll give just some quick examples. One basic scoring rule or heuristic is efficacy, which is just like the depth of the cut. So it's just the perpendicular distance from the LP optimum to the cut. And what it's suggesting is, the deeper cuts are like better. Another such scoring rule is objective parallelism, which is roughly just the angle between the cut and the objective vector. So just another measure that's suggesting that maybe you don't want to add cuts that are like super obtuse or something. Yes, just another measure. And then third example is directed cutoff distance is like efficacy. It's the distance from the LP optimum to the cut, but instead of perpendicular distance, it's in the distance of the best integer feasible solution found so far. So here the black vertex, the LP optimum, the white dot is the best integer feasible solution found so far. Then these two pictures, both cuts, the dashed lines, both cuts have the same depth, but the one on the left has a better directed cutoff since it's kind of closer to the best integer feasible solution. So we can kind of ask the same. We can pose the same learning problem. So instead of like learning cut parameters directly, maybe we want to learn like a mixture of these scoring rules to choose between cuts in a more informed way. And this is not something arbitrary. So this the fastest open source solver called Skip uses actually like a hard-coded combination of 4 different weights. So the first 3 are the ones I just presented, and the fourth is something else. And it uses a hard-coded combination. Yes.
You're generating a lot of these cuts and scoring each one to try to decide which one is the best to add. Why don't you just add all of them?
Yeah, so that's a great question. I don't know that there's a super good answer for that. Like, I think basically there's just this fine trade-off between adding too many cuts, because if you add a lot of cuts, then now you have just a bigger problem to deal with at every node of the tree, even though the tree might be smaller. So I think, yeah, I think solvers kind of, in no agreed upon way, just, yeah, they somehow decide upon how many cuts to add. Yeah, because, you know, and in some cases, the cut families can be very large. Like, you know, if you're generating some of these more structured cuts, so for example, if the integer program is like a knapsack style problem, there are like an exponential number of meaningful cuts that you can generate by just looking at the knapsack constraints. And you definitely wouldn't want to be adding all of them to the formulation. So it's not a very well understood problem. It's really the answer, I think.
An actual way of solving the problem, even a family of cuts, find the cut maximize the score.
Yeah, so I mean, like for the scores I presented, those things are just like formulas you can compute for every cut.
I was like, given a family of cuts, can I find a specific cut in that family that maximizes the score at random?
Oh, I see. Okay, so like you're asking like, so for example, Kvatal-Gomery cuts is this infinite family of cuts. Can you find I also don't know the answer to that. I mean, I don't think it's something that has been looked into either. And really in practice, you know, what you do is like, when you solve the LP relaxation, you get for free a set of Kvatal-Gomery cuts, a finite set. And all of those are pretty good. And whether or not to add all of them or a few of them is, it's all, yeah, I mean, it's like magic that they do, but you know, it's not really understood. Yeah.
Would the question of how many cuts to add also be the sort of heuristic that your learning system could learn effectively, or is that
Yeah, I bet it could. You know, it's not explicitly what we considered, but you know, I bet it could. But you know, it gets like more complicated because, you know, you don't want to be adding. So I think most solvers will add most of the cuts at the root, and then will add, like, you know, now and then add cuts throughout the tree. So you know, it's, yeah. That is also an interesting question. Okay, so just quickly, so this is a generalization guarantee for doing that kind of learning that I just mentioned. So you're no longer learning the cut parameter directly, but rather these like mixture parameters to do a more informed selection of the cuts. And again, I'm just presenting this for simplicity, for like using this to select a single CG cut at the root. And you know, in the pack learning sense, you know, this function family, you can think of it as like the class of functions which are like measuring the tree size as a function of mu1 through mu d. So each mu1 through mu d defines such a function in a class. Okay, and you know, here's like just a proof of concept, kind of showing that doing this kind of thing can be actually worthwhile. It's, you know, it's not just restricted to these generalization guarantees. Choosing this parameter in a distribution dependent way can have some interesting distribution dependent effects. So you know, here we're looking at two different distributions. They're both distributions over facility location integer programs. And what we're plotting here is, you know, we're using this parameter mu to control this mixture of two scoring rules. So it's the depth, the efficacy scoring rule, the parallelism scoring rule. And so how to interpret this plot is, for a given mu, the y value is showing the average tree size over 1,000 samples from this distribution. And you know, it's doing the same thing where, you know, for a given mu, it uses that mu to choose the best CG cut. And okay, and as Brian pointed out, we're using the Tableau guidance. So this is choosing the best CG cut from the finitely many CG cuts that the LP Tableau gives you. But you know, already just tuning that, it shows, you know, the best parameter, and when I say best, leading to the smallest tree size, the parameters that lead to the smallest tree size for the one distribution are actually the opposite of which what leads to the best tree size for the other distribution. Yeah, and you know, I think the question of, you know, if you were actually harnessing the power of this entire infinite family of CG cuts, then how do you optimize these scoring rules and pick? You know, that's I don't know how to do that. But I mean, I guess my guess is it's probably too difficult to do to make it worth incorporating into a branch and cuts framework. So like these these finite CG cuts that you get from the LP tableau are just so easy and fast to generate that I think, and you know, like when I say CG cuts, there are also these Gomery mixed integer cuts that you can also get from the tableau that are like even better. Okay, and then the final thing I'll just say is, you know, we present like a generalization of all this, a generalization of the generalization guarantees to handle a very general model of tree search. And you know, throughout this talk, I've only focused on this like very simplified setting where we add a single cut at the very beginning, add it to the formulation, and then run branch and bound. But really, you know, all of this stuff you can kind of generalize it to thinking about tuning some parameter that controls cuts being added throughout the tree. So here, you know, you can kind of abstract away and say, you know, there's some tree search algorithm that, you know, the input is, okay, instead of an integer program, it's just this abstract root node Q1. So that's the input. And then there's a few things that control how this tree search goes. At every step, you choose a node to expand next. That's given by some node selection score. So you choose the node that maximizes that. At every node, you take some action. So some action A, and then after you take that action, it'll be determined whether or not you stop at that node and move on, or you add some number of children to that node. And those children can depend on the action. So you can kind of vaguely see that, you know, this is going to capture like actions being cutting planes and the children being the branching, and the branching can depend on the cutting planes as well. And the important thing here, you know, is this whole search is parameterized by this parameter mu, which is saying, well, okay, we'll let the actions be chosen to maximize this action score, which is a convex combination of two other action scores. And, you know, this two could be any number of them. Okay, and for that kind of a very general model of tree search, you can kind of write down this generalization guarantee that is going to recover a lot of previous results on generalization guarantees for like learning to branch, learning to cut and whatnot. I mean, learning to cut meaning our own previous generalization guarantees. Yeah, and you know, it's just gonna look like this. It depends on like the maximum tree depth, branching factor of the tree, and the number of actions available at each node. So for example, if you're trying to choose between Quatel Gomery cuts generated from the simplex tableau, B is something like n, where n is the number of variables of the integer program. You know, k is just like 2, and then, you know, the depth is whatever, n or whatever. So yeah, and this is like the first guarantee that is, you know, able to handle multiple of these critical aspects of branch and cut, which is, you know, often what you're doing in practice. If when you tune these solvers, is you have some freedom to tune how the branching is done, how the cutting plane selection is done. You know, and previously these kinds of analysis had only focused on one of these aspects at a time. Okay, and that's all I have. So I'm happy to take any questions. Yeah.
Your experimental results for the facility location problems, what did the distributions that you used look like?
Yeah. Okay, so one of the, I believe the one on the right, that was just, we took some arbitrary facility location thing and then just perturbed like the costs and stuff by adding some Gaussian noise. So it's just, this is obtained by just perturbing a base facility location to generate the samples. The one on the left is a bit more structured. It comes from a facility location. So these facility location problems are generated by placing, so it's like a box of side length 1, so 0, 1 squared. And the facilities are evenly spaced on the line that divides that box into 2. So let me just draw this, right? So it's like this. The facilities are like this. And the facilities all have the same cost of 1 to build. And then the users are selected uniformly at random from this box. And the cost is just the Euclidean distance. So, and yeah, so interestingly, so, you know, this is saying that for this Euclidean distance kind of thing, it really pays to favor what parallelism, right? And then on the right, it pays to favor the depth of the cut.
So in the general setting, what are the things you are actually learning? I understand when you choose just the cut on top level, you will learn say what all boundary parameters and so on, and use it for the new one. But in the general case, what all are you learning
Mhm.
about?
Yeah, so really like the important things in branch and cut, I guess, are node selection, branching, and cutting plane selection. So first of all, even just if you just think about cutting plane selection, before everything I talked about was just like doing stuff at the root. So this lets you generalize then say, suppose you're controlling this mu, and it's actually going to now dictate which ones you added at. Like, you know, at any intermediate stage of branch and cut, you have some set of cutting planes that you can add from. And if you're allowing this mu to dictate which ones you pick at every stage, then we're able to handle that. And then you know, branching, yeah, that's like just it's a whole nother topic on like how to choose the variable to branch on. People have studied even, you know, like maybe you don't want to just branch on a single variable, but you actually come up with two hyperplanes that partition the entire feasible region in a way that's different from just branching on a single variable. So anything of that sort. Node selection, how it's like usually done, I think, is so like one reasonable way is to choose the node that has the best LP relaxation solution, and then explore that. But you know, like solvers will do a combination of that and like a combination of that and some level of depth first. So anything you can think of is, yeah.
Do these solvers in practice that you're talking about use this kind of performance tuning? And like, as you mentioned, this hard-coded, that sounds a bit weird, but like, are they finding those in the backend by doing everything, or?
Yeah, so, okay, yeah, like, so I guess, you know, that is, so one of the motivations here is that, you know, if you're solving some typical kind of integer program, like an auction design integer program, then, you know, you might as well try to tune something so that it does well in the distribution. Whereas, yeah, I guess, I mean, see, like these general purpose solvers, I mean, their goal is to just work well on anything. But I mean, I think some of these things also have started to come out with, I mean, maybe not like these things might have been around for a while now, but like automated parameter tuning kind of things. And I mean, you know, I should clarify, like, we're not giving any new algorithm or any new method to do parameter tuning. We're just saying, well, you know, these things don't really come with provable guarantees. So, you know, here are the accompanying provable guarantees. Yeah. Yeah.
So it seems like you're cheating a little bit with the y-axis here.
Oh yeah.
The cuts on the right-hand side just actually reduce the tree size a lot more than the cuts on the left-hand side.
Yeah. No, absolutely. Yeah.
Analysis of the space of cuts giving you any intuition for like when cutting is actually a good idea, or when it won't help with the problem as much, or is that kind of orthogonal?
So okay, let me just say, so these plots are solely to illustrate that it can have a difference, and that difference can be distribution dependent. So yeah, like on the left, really, it's not, you're not getting that much savings. Whereas, and you know, but I should clarify that this is just for a single cut at the root. And you know, in practice, you're going to be you want to add a lot more. And you know, we have other experiments and like knapsack problems where adding cuts throughout the tree, like it really doing and tuning the parameter in this way, like it really has a meaningful and dramatic relationship. But yeah, as to your question of like, do people know when are cuts even worth generating? I think, you know, I don't have a great answer for that. And I think it just falls into this realm of not understanding very well how to add these things in a principled way. I mean, there's a lot of theory about, you know, when cuts are strong in a sense of like they're facet defining for the convex hull of the integer solution. So there's a ton of theory on coming up with these things, but in practice, there's this very fine trade-off about how much time you're spending to come up with these cuts, how many you add, and then ultimately the goal is to have, you know, finish running quickly. So even if you are able to generate a cut that lets you solve the LP relaxation and have an integral node, but it takes forever to find that cut, then that's obviously not worth doing. Yeah.
You're a balance on like the number of hyperplanes that define the that extension.
Yeah, this is a good question. So first of all, Kvatal-Gomery cuts only work for pure integer programs, but you know this. I think it all should. I like spent a little bit of time thinking about that and thought to myself, you know, it probably all extends to mixed integer programming. So I think the key part is like there's a part in analysis when we're thinking about pruning due to integrality. So when the two cuts, you know, if you've added a cut and at some node you solve the LP relaxation, it happens to be integral. When the two cuts like sort of lead to that same behavior. And in that analysis, you kind of enumerate over potential like integer hull solutions. And you know, I bet in the mixed integer case, you would just look at the mixed integer hull and look at maybe the places it intersects. I mean, of course, now an infinite number of feasible solutions, but so, okay, right. So see, Kvatal-Gomery cuts, this rounding step, it really relies on the fact that the points all have integer values. But yeah, so there are these things called Gomery mixed integer cuts, which they generalize Kvatal-Gomery cuts to work for mixed integer programs, but they're not just in generalization, they're actually just better. So you can use Gomery mixed integer cuts for a pure integer program, and it's like it strictly dominates the Kvatal-Gomery cut. So yeah, so Gomery mixed integer cuts is, you know, that was the main, I guess the main application of our like structural analysis. I never defined what they are because it's just like a slightly technical thing, but it's, you know, similar rounding kind of logic. But yeah, Gomery mixed integer cuts are like, if you run Cplex or Gurobi or whatever, it'll be adding many of these things throughout. And I guess that was considered like a real breakthrough because I guess people didn't think that this kind of cut that doesn't take into account any structure could compete with, you know, if you have an integer program that it's based off of some graph problem, then, you know, there are very specific cuts you can kind of look at the graph structure. You know, if it's like some kind of independent set thing, there are these like clique kind of things you can write down. And people were like, well, there's no way this general purpose rounding kind of thing is going to be anywhere as good as those kind of things. But it turns out in practice, they're just so easy and quick to generate and end up being quite good as well. Yeah, and another thing is, you know, you can generate these things in like rounds where if you're at like, say you're at the root and you add a bunch of CG cuts or Gomery mixed integer cuts, so you add all of them, then you can resolve the linear programming relaxations, find the new LP optimum. And then by doing that, you now for free get another set of these cuts that will all separate that new optimum. So it's all like this balancing between, you know, how much time do you want to spend doing that, and how much time when, you know, like any time you spend doing that, you could also be expanding the tree and searching through the tree. So, and all of those kind of parameters that control how much time you're spending can be tweaked in these solvers.
Yep, next time, sit again for the talk.